This video explains the working model and simulation of floating point MAC unit, multiply accumulate unit. The basic operation of multiply and accumulate unit is that we can have multiple inputs, let's say A1, B1, A2, B2, A3, B3 and so on. So the first set of inputs are multiplied and then added to the next set of inputs. That is A1 into B1 plus A2 into B2 plus A3 into B3 and so on. This is how the MAC operation happens. This module float underscore MAC is for floating point multiply accumulate unit. So the numbers the inputs or the numbers A and B are of floating point representation with the exponent and mantissa as 8-bit and 23-bit. Here we have considered single precision floating point number representation, wherein we have 1 sign bit, 8 exponent bits and 23 mantissa bits. AZ and BZ are the hidden bits. C is the output and CZ is the hidden bit of the mantissa output mantissa. So as the MAC operation is, we need to multiply the two inputs A and B, and we need to add the previous input to the present input plus A2 B2. So initially we'll have to give a reset condition that gives 0 as the output and 0 to be added with A1 plus B1, and then we proceed on with the result of A1 into B1 plus A2 into B2 and so on. For this we need a feedback with a flip-flop to store the previous value. So we have also designed a D flip-flop. Now the design of floating point multiplier is basically two steps: the exponent equalization or exponent normalization, and then the mantissa multiplication. So multiplier underscore signed is an integer multiplication module which is designed based on the Wallace tree structures. And recurse3 underscore signed is an adder cum subtractor module which is designed based on prefix adder. This float underscore mult is the module which does floating point multiplication. Coming to floating point addition, again we have three steps over here. One is exponent normalization or equalization, and then we need to shift the mantissa, and again we need to add the mantissas. So as explained, recurse underscore signed is an integer addition module. This part gives the exponent equalization or normalization, and this part gives the mantissa shifting and addition. So utilizing all the modules called floating point multiplier, floating point adder and D flip-flop. This D flip-flop is also given an enable signal where you have one clock, enable, reset condition, and the input and the output. Basing on these modules, the floating point MAC is designed. So now let us look into the test bench of this floating point MAC. Initially, we have included all the submodules required for the floating point MAC unit. The parameter MNT and EXP defines the mantissa and exponent resolution, that is 23 bits and 8 bits. We need to define the clock, enable, reset conditions as well. So now we have instantiated the top module float underscore MAC, which is the design under test over here. So the initial conditions should be taken care of well, because we are depending upon the reset and clock. So we have to get a proper reset condition until which we do not get the correct output. If the initial reset is not proper, the output might be incorrect. So what we have done, we have initially taken clock 1 and reset as 1. So here reset is equal to 1 means the complete circuit will be resetted and the output would be 0. And the initial outputs were 0. And then after some delay, we have made reset is equal to 0. Now coming to this is a clock generation part wherein initial clock was 1. So for every CK is declared over here as 10. For every 10 units of time, the clock is inverted. So we get a pulse waveform wherein we have each clock width will be of 10. 10 time units of delay. So coming to the actual inputs, the first set of inputs were A equal to 0 and B equal to 0. So after some delay of 5 units, I have given A as 18.0 and B as 9.5. Here the representation is in binary is this way. A of 31 and B of 31 are the sign bits of A and B. A of 30 to 23 and B of 30 to 23 are the exponent bits, and these two are the 23 bits are the mantissa bits. So after a delay of 10, that is at 20th clock at 20th time of clock, I am giving these inputs. So now our result should be something equivalent to this. So initially we had 0, so that 0 should be added to this 171. That is, these two numbers should be multiplied and to be added to 0. That is 171. And then in the next clock cycle, or next set of the inputs were 4.5 and 2.2, which results in the multiplication of 9.9. So our final result should be something like this: 0 plus 171 plus 9.9, which results to 180.9. So now let us check the simulation of this module. For that, we'll be opening a command prompt in the same folder. The simulation is being done using iCaris Verilog, and the command is given here. So iVerilog is the command used, and -G 2001 is for the version specification. Since I have given all the submodule names over here in the test bench itself, I need not mention specifically over here in the command. So now to view the output, we'll have to generate the VCD dump file, and this we'll be viewing using the waveform viewer, GTK wave. Value change dump file will be generated from the test bench using the command $dump file, and yes. So now first let us look into the let us insert the clock, and then let us insert the reset, enable, and now if we can see over here, as I've given, the reset was initially 0, initially 1, and I have made it to 0 after some delay. That is exactly at #3 I have made it to 0, so at 3 seconds it was 0. And enable, I have taken it always as 1, and the clock period is 10, or rather it is 20. The complete clock period is 20. So one cycle is 10 and the other cycle is 10. Coming to the inputs, A, B, and C is an output. So now initially our inputs A and B are 0 and 0. Output is also 0. And then the inputs are given as 18 and 9.5. The output should be equivalent to 171. Now let's check whether this hexadecimal value is equivalent to 171. 432B40. This is equivalent to 171. So the first output is right, and then coming to the second output, so this 0 and this 171 should be added with the multiplication result of these two inputs. The multiplication result of those two inputs is 9.9, and now adding up 171 and 9.9 should result in 180.9. So let's check whether this 4334E666